evaluation strategy. So very often that we call a sub-expressions of a lambda expression of the shape of have a lambda abstraction that apply to another lambda expression is called a redex. Okay, it actually is a shorthand for reducible expression. So the strategy for actually running any lambda calculus program is to look for all the redex in the program and rewrite them by applying the beta reduction rule. Of course, we have to need to do some alpha renaming if there's any clash of variable name. Okay, but even by doing so, we still have multiple ways of doing that. Okay, for example, there are at least two ways of running the beta reduction in case that we have multiple redex that we can spot in a particular lambda calculus program. Okay, one way is to do innermost and leftmost, which means that we always look at the lambda expression as a syntax tree, and we always look at the innermost and leftmost redex, and we apply the beta reduction first. So sometimes this is also called the applicative order reduction. Okay. Another alternative is to look at the outermost, leftmost redex that in the current program, and we apply beta reductions. This is called the normal order reduction. We consider this lambda program that we have a applications that this lambda abstractions to the second one, which is from y to y, and the first one is even more complicated because you have some nested abstractions inside. Okay, it's a function body. Okay, so let's consider if we run this program using innermost leftmost strategy, which is applicative order reductions. So we first look into the entire expression for the innermost leftmost, which is this one. Okay, this is a leftmost innermost redex. Okay, assuming that we are conduct some like alpha renaming as well. Say this is x1. Okay, this is x2, so this will be x2, this will be x1. So if we apply the beta reductions to this redex, this will give us actually that returns x1. Okay, so which is the outermost x. So this whole term will be reduced into this one. Okay, lambda x return x. So again, this is the outer x. Okay, x1, and then we then look at this redex, and then of course obviously this will give us lambda y equals to y. Okay, for the same program, if we apply the outermost leftmost strategy, which is normal order reductions, we will consider this outermost redex, okay, to reduce. So we simply replace this x1, okay, by this actual argument, which is lambda y equal to y. Okay, and we already performed the renaming. We rename the this inner x to become z. Okay, so so now no more x1 x2, this is x, this will become z, and then we get the foreign term, which get back like lambda z equal to z, that applies to lambda y equals to y. So and we again applies the beta reduction to this redex, we get the final value, which is lambda y equals to y. Interesting facts that about the two different evaluation strategy. Okay, the first note that we have is that they do have some connection with the real-world language. For example, the call by value semantics, which is found in languages such as Python or C or C++ or even Java, is basically applicative order reduction, except that we don't evaluate the redex under lambda abstractions. Okay, basically given a function, we do not look into the body of the functions to reduce anything until the function is being applied. So that is called by value semantics, very similar to the applicative order reductions. On the other hand, for the normal order reductions is actually similar to something what we call the call by name semantics, which can be found in languages such as Haskell. For example, Haskell we have a lazy semantics is because it's called by name semantics. So you can actually see why it is lazy by following the normal order reductions. But again, there's some minor difference between the two, because like for call by name semantics, we do not evaluate the redex under the lambda abstractions. Okay, and then when we compare applicative order reduction or normal order reductions, which one is better? Okay, so we actually found this a very useful theorem by Church and Russell. It says that like if a lambda term can be evaluated in two different ways, and both ways would terminate, and both would actually give you the same result. So it doesn't matter which order you choose. If a lambda term terminates, okay, eventually they will give you the same result. Okay, so for example, we have seen the earlier example, they have give up the same output. Okay, then you talk about non-terminations. Okay, just now in the second notes we mentioned that, well, they would produce the same result if the programs are terminating, right? But then you argue, hey, how can a lambda program be non-terminating? Okay, well, actually, in fact, there are programs that can be expressed in lambda calculus that could be non-terminating. For example, consider this funny program that we have this weird lambda abstraction applied to itself, and if we try to apply the alpha renaming and then beta reductions, and we work out the math, we get back the same term, and this will go on and on forever. Okay, so this is a non-terminating lambda calculus program. So that relates to the third note that we want to argue. The normal order reduction seems to be computationally more expensive, but the strength for that is that it's more likely to terminate compared to applicative order reduction. For example, consider this program. If we apply normal order reductions, we will actually ignore the fact that the actual argument that eventually be bound to x is non-terminating, because for normal order reductions we will reduce the outermost redex, and that would immediately drop this part, this non-terminating that we have learned from the last slide. Okay, whereas compared to applicative order reductions, we will still have to compute the innermost redex. In this case, this is one we first trigger, and this would use a non-terminating behavior. And that's why in Haskell we have lazy semantics, and sometimes we are able to express power to write program that can work on infinite data structures. That's due to the property of normal order reduction.